Today I'm going to be talking about the conservation of energy. Now, first off, the conservation of energy states that the total amount of energy in a system remains constant, as in it doesn't change. However, energy within a system can change from one form to another. Using this equation here, you have potential and kinetic energy both before and after something happens to it. In our experiment, that will be dropping a ball from a certain height until it hits the ground. The conservation throughout the energy throughout the entire experiment remains constant, but the type of energy that it is changes. So we will be dropping a ball and throwing a ball out of a window to measure different things about that ball and about the system. And we will be throwing it from a certain height that will be both measured using this picture and we will be using a stopwatch in real time to time how long it takes the ball from when it is dropped or thrown to when it hits the ground. And we will also be determining the height using the time using one of our equations of constant acceleration. So we will be figuring the height both ways. So here, T is on both sides of the energy equation. This is kinetic energy, and this is 1/2 mv squared. So we're going to be using the mass of whatever it is we're throwing or dropping, and then the velocity that it is at the beginning or the end, or really at any moment that we're looking at. In our equation here in our experiment, we're only going to be looking at the velocity at the very beginning, which in the case of it being dropped will be 0, and at the very end. Here, V, this is potential energy. This is mgh, that is mass and acceleration due to gravity and the height at which it is being thrown or dropped. This value will start out at a rather high number and decrease down to 0 as the height goes to 0 relative to the ground. So first I'll talk about our apparatus. Our so-called apparatus consisted of dropping and then throwing a soccer ball and then a tennis ball from the top story of Tyler Hall. And then we videoed that and then timed how long it took for the ball to fall or be thrown down from the time when it was released to when it hit the ground. So here are the times for the soccer ball and the tennis ball. These were so close that we just averaged them and then used that time to find the height at which we dropped those. So here we have the equation, or one of the equations of motion, the constant acceleration. And so our final height is 0, and we are going to be looking for our initial height. So, and this being with the initial velocity being 0. So all we have here is 1/2 and then 32, because we're going to be using feet in this experiment. And then the time, the average time of the drop of the soccer ball and the tennis ball. So 1.4 seconds, so that's squared. So our initial height was 31.36 feet. So, and we could find that without using a measuring tape or anything else, just by using time in this equation here. So now we're going to find the final velocity at the ball, the velocity at which the ball hit the ground. So then again, we use one of our equations of motion. Velocity equals v naught plus acceleration times time. Again, this being with the initial velocity being 0. So 32 times this we're going to be using the soccer ball in here, time 1.41 seconds. So the final speed, the speed at which, or the velocity rather, of which the soccer ball hit the ground was 45.12 feet per second. So now we will look at an equation of energy to show that energy is being conserved. So the equation of conservation of energy is kinetic energy plus potential energy equals final kinetic and potential energy. So because there was no initial velocity on the ball in the first drop of the soccer ball and both the tennis ball, the initial kinetic energy is 0, and the height is going to be 0 at final, so that the potential energy in all of these experiments is going to be 0. So that leaves us with just mgh equals 1/2 mv squared. So the reason why we did it with a tennis ball and a soccer ball is to show that the mass of what is being dropped is irrelevant. So you can see that here in the times being so very close, and this just being, 2/100ths of a second. It's just a tiny bit of experimental error there. So it's going to be the same. Mass is irrelevant. The soccer ball is much heavier, but it doesn't matter. Here we show that mathematically. We show mathematically that the mass is irrelevant. So we're just going to have gravity, the height at which was dropped, and then we can find the final velocity here. So then we just find the velocity, square root of 2 times gh, 44.8. This number is slightly less than what we found up here, but we're going to talk about that later. So right now we're going to look at the ball that was thrown down. So this time, the time of which it took the ball to hit the ground here was 0.6 seconds. So here we're going to find first we're going to find the initial velocity at which this was thrown. So again, just as we did in the first one, here we're going to use equation of motion of constant acceleration. So y, or the final height, equals the initial height, the speed and the acceleration there as well. So we plug in 0 for the final height that hits the ground, and that's going to equal the initial height here that we started with, looking for the initial velocity. So we plug in this using 32 again because we're using feet, and the initial velocity, which we get, is 42.67 feet per second. So that's the initial. Now we're going to look for the final velocity of the ball being thrown down. So then we just use, again, this is the velocity equation of the constant acceleration, v0 plus constant acceleration times time. So we use the initial velocity plus gravity with the time. So here we get a final velocity of 61.87 feet per second. Now again, we're going to look at conservation of energy. So again, the final potential energy is going to be 0. The initial kinetic energy, we're going to actually use that in this one because there's some initial velocity. So again, mass is irrelevant. So we plug in our numbers here, and we get final velocity of 61.87 feet per second. So this number here is basically the exact same as this. Mathematically here it's shown as exactly the same. The reason for that is because the air resistance, the friction, the work done by friction of the air on the ball didn't have very much time to work on this. It only had 0.6 seconds, so mathematically it looks like it didn't do anything. It did, of course, do something because there is air. But mathematically, and with the time that we found, it looks as though it didn't. Over here, though, the time being more than twice as long, you can see the effect of the work that the friction did on the ball here. So in the conservation of energy, you would end up with work being done by friction, and that is why this speed is less than this one. So as you can see though, throughout, energy is conserved, and this is the experiment that we used to prove.